At the end of the last session, we organized the packet in a detailed and comprehensive manner as follows. The start of text, STX, is AF in hexadecimal. The end of text, ETX, is 7 in hexadecimal. And the length corresponding to the second LAN will include the length of the command, CMD, data, checksum, and so on to make parsing easier later. Next, the command, CMD, can be defined variably and the checksum for the data part. The checksum will be calculated by performing a bitwise XOR operation from the start of text, STX, up to the data before the checksum. I will write the code for this on the Arduino side. First, for the serial communication, the start of text, STX, is set to 0xaf, which is a hexadecimal value representing the start of the communication sequence, followed by the end of text, ETX, which is 0x7d, another hexadecimal value indicating the end of the communication sequence. Now, we will insert one piece of data, so we will input D0, which is a hexadecimal representation of the data to be transmitted. Therefore, the length should be 1, 2, 3, 4, indicating the number of bytes in the data sequence. Let's start by inserting the length, and then we will set the command CMD to 1, which is the command identifier, the data to 2, which is the data value, and the checksum to 0, which is used for error checking. When you are sending data, it can be transmitted in this manner as well. For instance, you can use the serial.writeBuff function. At this moment, the size of the data being sent is, when uploaded, the Arduino sends this byte to the PC, and since viewing it in hexadecimal is more accurate, we will use a terminal program called CoolTerm instead of the serial monitor. Please run it using either PuTTY or CoolTerm, where you can view it in hexadecimal format. In CoolTerm, make sure that the port settings are correctly configured to baud rate in the options and that data has been properly received. But since this is not in ASCII format, it breaks the data into segments. Let us switch to view hex mode. Clear the view once and then try resetting it again. When you reset, you can see the data coming in as AF04, AF01, AF02, AF0, AF07. However, in this case, I set the checksum to 0 without calculating it, so I did it this way. However, for now, I'm just showing that packets can be sent this way, but honestly, this is not the right approach. Now, if I say I'm going to send a packet, it makes sense to create a library for packets so that I can easily set the data and command, CMD, each time and send them conveniently. So, I will be writing the packet library now. To begin, open a new sketch in your preferred software once you have your blank canvas ready. The first step is crucial, since there is a considerable amount of information to cover regarding the step and the packet header. It is essential to spread out the details clearly and methodically. Start by outlining the main points you need to address. This will help in organizing your thoughts and ensuring that nothing important is missed. Next, break down each section into smaller, manageable parts. For instance, when discussing the packet header, you might want to explain each field individually, providing examples and illustrations where necessary. This approach not only makes the information more digestible, but also ensures that your audience can follow along easily. Remember, clarity and to begin with, the first step I will take is to set up the necessary variables. Following that, in my particular scenario, I will proceed to organize these variables by defining them as macro constants. This will be accomplished using the define directive, which is a preprocessor command in the C programming language. By doing so, I ensure that these constants are set up correctly and can be used throughout the code without any issues. This method helps in maintaining consistency and avoiding potential errors that might arise from hard coding values directly into the code. After the start of text stx, we will first define 001AF as we planned, and then organize it as define packet end of text ETX 007D. Next, we will proceed to create a packet command, often abbreviated as CMD, where the variable A is set to 0. The variables B, C, 1 and 2 will vary depending on the specific hardware configuration you are working with. For the purposes of this explanation, I will assume that the command includes the variables A, B, and C, and I will set A to 0. Today, our focus will be solely on the creation of the packet itself. In the context of the Eastern Void package, we will input the generated CMD value, and subsequently we will receive it as a random pointer. The first step involves saving this pointer. Following that, we will initiate the process with packet C, starting with the header block and the packet header. We will then proceed to create a buffer designated for the start of text, commonly referred to as STX. This will be followed by the creation of the data array, after which we will receive the array pointer value. This pointer value will be instrumental in forming the packet structure. Specifically, the first position of the pointer will correspond to the packet STX, while the second position will be assigned a random value. However, it is important to note that this random value will actually represent the length of the array variable. To elaborate further, the packet command, CMD, is a crucial component in the communication protocol, and its proper configuration is essential for the accurate transmission of data. The variables A, B, and C play specific roles in this process, with A being a constant in this scenario. The Eastern Void package serves as a framework within which the CMD value is processed and interpreted. By saving the pointer initially, we ensure that the subsequent steps are based on a stable reference point. The creation of the buffer for STX is a preparatory step that facilitates the organization of the data array. The data array itself is a structured collection of information that will be transmitted. The array pointer value is a critical element that helps in mapping the data within the packet structure. The assignment of the first position of the pointer to the packet STX ensures that the start of the text is clearly defined. The random value assigned to the second position, while seemingly arbitrary, is actually a calculated representation of the array's length, ensuring that the packet structure is both accurate and efficient. Now, if we assume that there is a length value with the current array variable, and if there is just one D0, then it would be 6 bytes. So this would result in a value of 6. But actual value that will go into rand is 1, 2, 3, 4. So the value rand becomes this. Value excluding the start of text, STX, and rand. Considering the addition of D1 and D2, then this would be the case. We will perform operations in such a way that ultimately it corresponds to 4 among 0, 1, 2, 3, 4, 5. This means that we will be focusing on these specific numbers and ensuring that our operations align with them. So, numerically, if we calculate, the data rank is originally the last position, and then this is the checksum CS position. The CS position is crucial because it helps in verifying the integrity of the data. Therefore, we will first insert the fixed value into the CS position, ensuring that the data is correctly validated. After that, we will input the packet start of text STX value, which marks the beginning of the data packet. The reason we do not start from 0 is that we will be inserting X and Y operations here, which are essential for the process, so the CS will not be included. This approach ensures that our operations are precise and accurate, and that the final result is as expected. By following this method, we can guarantee that the data is processed correctly and efficiently, leading to reliable outcomes. By doing it this way, the checksum CS value is now calculated. Finally, data plus rank. In this way, I have now created the rival and the packet. Next, I will just simply copy this. I will intentionally pretend that I am creating a new fight, and the data currently consists of the numbers 0, 1, 2, 3. The data starting from 3 is exactly what we are referring to. But since we're going to put in one piece of data, let's just try putting CA here, buff. First, you need to insert 3 Romex CA components. After that, proceed with the packet header, followed by packet generate, and then packet CNDA. Make sure to use size of buff and buff pointer in the specified order. Once you have completed these steps, compile the code. There should be no errors if everything is done correctly. After compiling, you can upload the code. It seems to be connected. Here now. This process ensures that the system is set up correctly and all components are functioning as expected. If you encounter any issues, double-check each step to ensure accuracy. Proper insertion and compilation are crucial for the system's performance. First, let's disconnect from the current network, then upload the necessary files. And finally, check everything thoroughly here. Clear and connect. Now, since it briefly disconnects in the middle, it has turned out like this. After clearing and being in a connected state when riveting, let me just check it once. So the last AF and STX came in correctly, right? The last ETX 7D came in exactly, right? LAN 1, 2, 3, 4, that's 4, correct? Since we have a CMD, 0 came in. Since we have set up the data CA, it has come in right. After that, the checksum is probably correct. In this way, we can send packets. Today I will only focus on the basics. I created a packet according to the protocol we made last time and transmitted it from the Arduino to the PC. In the next session, we will need to parse the remaining part of the packet, even if we send it. Usually, it's called parsing, and we need to read the data. So, we will use 2 Arduinos. One will send data, and the other will receive the data and parse it to verify. I will see you next time.